So the next functional group we're going to discuss are aldehydes and ketones, and both contain a carbonyl group. Now, a carbonyl group is a carbon double bonded to an oxygen, and that carbon can be bonded to two other things. An aldehyde differs from a ketone because of the location of this carbonyl group on the chain. An aldehyde has this C double bond O at the end of a chain, so that the carbon has at least one hydrogen bonded to it. The other bond could go to the rest of a chain or to another hydrogen. A ketone has the carbonyl bonded to at least two carbons, well, only two carbons. When we name an aldehyde, or when the carbonyl has at least one hydrogen bonded to it, so the carbonyl is on a terminal carbon or an end carbon, we take the parent chain and replace the E of the alkane name with Al, or Al. So the carbonyl group is always carbon 1, so we don't need to number it. We always start on numbering from that carbonyl group anyways, so there's no need to specify. So the structure on the left is 5 carbons long, 1, 2, 3, 4, 5. If it were an alkane, I would call that pentane. But since we have C double bond O on a final carbon, that carbon has at least one hydrogen to it, we know that it's an aldehyde. So we call that pentanal. The structure on the right is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, no matter which way you count. This chain is 6 carbons long. And with a 2-carbon substituent on carbon 1, 2, 3, 4, that gives us 4-ethylhexanal. For drawing, we just work backwards. We see Al at the end. We know it's an aldehyde. And we see bute, which is 4 carbons long. So butanal would look something like that. In our second example, it's also an aldehyde with the Al ending. However, the parent chain is going to be 5 carbons long. Our name also tells us we have a methyl group at carbon 4, and since we always start numbering from the aldehyde end, our methyl group is going to attach to this carbon here. And here we have 4-methyl pentanal. Ketones are very similar, only to denote that our carbonyl group is in the middle of a chain, we need to replace that E of the parent chain with ONE, or own. So for ketones, we do need to designate with a number what carbon that carbonyl is attached to, because it's somewhere in the middle of the chain. However, we only need to do it if there's more than 4 carbons in our parent chain. That's because the smallest ketone, propanone, which is 3 carbons long, can only be on carbon 2, because otherwise, if it was on the end, it would be an aldehyde. And for butanone, if we put it on carbon 2 versus here on carbon 3, which would give us this compound, it's the same. This one equals this one. It's just upside down. Alright, so this compound on the right is 1, 2, 3, 4, 5, 6 carbons long, so we know we're dealing with hexane something on. And as usual, we want to number from the side that gives the lowest priority to our functional group, so that gives our carbonyl here the lowest number, so we are going to end up with hexane 3-one. The compound here on the right, again, the longest chain is 1, 2, 3, 4, 5, 6, 7. So we're at heptane something on, because we have a ketone here. It's a carbonyl in the middle of a chain. But we also have to account for the substituent. So we can see that it's a 1-carbon substituent on carbon 3. And again, we have a 7-carbon chain, so our final name is going to be 3-methylheptane-3-one. Alright, so let's draw 4-methylheptane-3-one. I just realized how similar that one is to the one we just named, so it should be easy peasy lemon squeezy. So if we know we need a 7-carbon chain because we have hept, not sept, and our ketone, denoted by ONE, is on carbon 3, and the last thing we need is a methyl group on carbon 4. So let's put that there, and then we just need to fill in our hydrogens. And we have 4-methylheptane-3-one. Our next compound, 4-hydroxypentantuone, we can start with our 5-carbon chain from pent. And we know that our ketone from the -one ending is on carbon 2. There it goes. And we have a hydroxy substituent on carbon 4. And we know that hydroxyl is an OH group. So on carbon 4, we just put our OH. There we go. So the properties of aldehydes and ketones are given to them by their carbonyl groups, their C double bond O. And because the electronegativity difference between the carbon and the oxygen, they are polar, so they exhibit dipole-dipole attractions with one another. They have lower boiling points than alcohols with a similar length of carbon chain because they're not able to hydrogen bond. However, their dipole-dipole attractions do give them more solubility in water than the very nonpolar alkanes, but because they can't hydrogen bond, they're less soluble than alcohols. And again, the longer the hydrocarbon chain, just like we saw previously with alcohols, the less soluble they are, less soluble the aldehyde and the ketone become, because the non-polar properties of that hydrocarbon chain begin to outweigh the polar properties of the carbonyl group. So we're going to look at 2 different reactions involving aldehyde and ketones. One is a controlled oxidation, which you're going to see looks very similar to an elimination reaction. We're also going to look at hydrogenation, which looks very similar to the addition reaction involving H2 that we saw before. But instead of adding things across a carbon-carbon double bond or taking them away from a carbon-carbon single bond, we're going to be adding and eliminating across a carbon-oxygen bond. So the first reaction we're going to look at is the controlled oxidation of alcohols to form aldehydes and ketones. We call it a controlled oxidation because we're not burning it all with oxygen all the way to carbon dioxide and water. Now, when primary alcohols undergo controlled oxidation, they form aldehydes, and we know from the previous video that a primary alcohol is one in which the hydroxyl group is attached to a carbon that itself is only attached to one other carbon. An example of this would be ethanol. The hydroxyl group is attached to a carbon which is attached to only one other carbon. So the oxygen in these oxidation reactions, often called active oxygen, is supplied by an oxidizing agent. And these are oxygen-rich compounds such as potassium dichromate, potassium permanganate, or hydrogen peroxide. On a test, you'd only be required to write square brackets around an O to indicate that it's an active oxygen or an oxidizing agent. Now what happens during the course of this reaction is that the oxygen atom and one of the hydrogen atoms remain on the carbon atom to make the carbonyl. In this case, because it's the terminal carbon, it's going to form an aldehyde. Now the 2 hydrogen atoms are removed and bonded with the oxygen from the oxidizing agent to produce water. So we remove these 2 hydrogens and a double bond forms in their place, and we make a molecule of water using the 2 hydrogens and the oxygen from the oxidizing agent. And we get ethanol, our aldehyde. The controlled oxidation of secondary alcohols, where the carbon that the hydroxyl group is attached to 2 other carbons, so this carbon is attached to 2 other carbons, is very similar to that of primary alcohols. But instead of forming aldehydes, secondary alcohols lead to ketones. In this case, our secondary alcohol is propantuol, and we see 1 hydrogen atom removed from the hydroxyl group. The second hydrogen atom is removed from the carbon to which the OH group is bonded, and we get a ketone where the carbonyl group, or the carbon double bonded to the oxygen, is that same carbon 2. So we have propanone, which is a ketone. The oxygen from the active oxygen, or the oxidizing agent, combines with the 2 hydrogens that we eliminated. It's an elimination, so we end up with a double bond, and also we form water from those 2 eliminated hydrogen atoms. So we know that primary alcohols lead to aldehydes, secondary alcohols lead to ketones, but tertiary alcohols, where the carbon that has the hydroxyl group is attached to 3 other carbons, are not easily oxidized. In fact, if we try to oxidize tertiary alcohols, we get no reaction. And this is because even though we have a hydrogen to remove from the hydroxyl group like we did with primary and secondary alcohols, there's no hydrogen atoms to remove from the carbon in order to form the water. So in an elimination reaction, we need to remove one atom from either side of where that double bond ends up. We have an atom to remove on the oxygen side of the future double bond, but we have no hydrogen to remove on the carbon side of the future double bond, because this carbon is bonded to 3 other carbons instead. So the hydrogenation of aldehydes and ketones is similar to the hydrogenation of double bonds that we saw previously, but it involves the addition of hydrogen, or H2, across a carbon-oxygen bond instead of across a carbon-carbon double bond. So in a normal carbon-carbon double bond, we add 1 hydrogen to a carbon on each side. But in this case, we're adding 1 hydrogen to the oxygen of our double bond and 1 hydrogen to the carbon of our double bond. So we're breaking a double bond as we did before, but we're breaking the double bond of a carbonyl between a carbon and an oxygen. So if we take ethanol, which is an example of an aldehyde, and add H2 under heat and pressure as catalysts, 1 H is going to add on to the oxygen, 1 of these H's is going to add on to the carbon, so we're going to lose this double bond because carbon can only be bonded to 4 things. So we see that we've gained 1 hydrogen attached to the oxygen to make a hydroxyl group, and 1 hydrogen ends up on the carbon because we've broken the double bond, and carbon still needs to be bonded to 4 things. So 1 ends up here, as you see, and 1 ends up here, as you see. And we end up with ethanol, which is a primary alcohol. So aldehydes lead to primary alcohols. The reaction is similar when we have a ketone like propanone. When we add hydrogen or H2 with heat and pressure as a catalyst, 1 of our hydrogens adds to the oxygen, the other of our hydrogens adds to the carbon. We lose this double bond, but in this case we gain a secondary alcohol like propan-2-ol, because the carbon that our hydroxyl group is attached to 2 other carbons.